Gold is one of the rarest elements in Earth's crust, yet it has been found on every continent, in mountains, deserts, and riverbeds shaped millions of years apart. This alone poses a fundamental geological question. How does a metal so scarce become so precisely concentrated? The answer is not chance, nor luck, but a sequence of geological decisions made by the Earth itself, decisions recorded in rock structures, mineral chemistry, and ancient fluid pathways. To understand where gold is found, one must first learn how the planet hides its most valuable materials. How geologists identify gold deposits, from rock types to modern exploration techniques. Gold has occupied a unique position in human history, not merely as a precious metal but as a geological signal, an indicator of specific processes that operate deep within the Earth. To identify gold deposits is not to search randomly, but to read the physical and chemical language of rocks, structures, and fluids. This chapter-style presentation examines how geologists understand, locate, and evaluate gold deposits, progressing from fundamental geological principles to modern exploration technologies. 1. Gold as a geological element. Gold is a siderophile element with a strong affinity for metallic bonding, yet it is most commonly found in the Earth's crust in extremely low concentrations. Average crustal abundance is approximately 0.004 parts per million, making economically viable concentrations the result of extraordinary geological enrichment. Gold does not form large, continuous layers. Instead, it is concentrated by hydrothermal fluids, magmatic differentiation, weathering, and sedimentary processes. Understanding where gold is found begins with understanding how the Earth transports and traps fluids under pressure and heat. Gold is chemically inert, resistant to oxidation, and highly dense. These properties explain both its preservation over geological time and its accumulation in secondary environments such as river gravels. However, primary gold deposits are the true targets of modern exploration, as they represent the original source systems. 2. Major types of gold deposits. Gold deposits are classified according to their geological setting, formation process, and host rocks. Each type carries a distinct exploration signature. Orogenic gold deposits. Orogenic deposits are among the most significant sources of gold globally. They form during mountain building events, where compressional tectonics generate deep-seated faults. Hot, gold-bearing fluids migrate upward along these structures and precipitate gold in quartz veins. Typical host rocks include metamorphic schists, greenstones, and altered volcanic sequences. These deposits are structurally controlled, making fault mapping and structural interpretation essential exploration tools. Epithermal gold deposits. Epithermal systems form at shallow crustal levels, typically less than 1.5 kilometers depth, and are associated with volcanic activity. They are divided into high sulfidation and low sulfidation systems, each defined by fluid chemistry and alteration minerals. Epithermal deposits often display strong surface expressions such as silicification, clay alteration, and anomalous mercury or arsenic values. Their relatively shallow nature makes them attractive exploration targets. Placer gold deposits. Placer deposits are secondary accumulations formed through mechanical weathering. As gold erodes from primary sources, it is transported by water and concentrated in riverbeds, alluvial fans, and coastal environments. While historically important, placers today serve an additional role. They act as geochemical indicators, pointing toward undiscovered primary deposits upstream. 3. Host rocks and structural controls. Gold rarely occurs randomly within rock units. Instead, it is concentrated where permeability, chemistry, and stress conditions align. Favorable host rocks often include mafic and ultramafic volcanic rocks, carbonaceous sediments, iron-rich formations, reactive carbonate units. Structures such as faults, shear zones, folds, and fractures are critical. These features provide pathways for fluid flow and sites for pressure drops, which trigger gold precipitation. In exploration geology, structure is often more important than lithology. Understanding regional tectonic history allows geologists to predict where these structures are most likely preserved. 4. Alteration patterns and pathfinders. Hydrothermal alteration is the footprint left behind by mineralizing fluids. Identifying alteration halos is one of the most reliable methods of narrowing exploration targets. Common alteration types associated with gold include silicification. Sericitization, carbonatization, sulfidation. Gold itself may be invisible, but associated elements, known as pathfinder elements, are more abundant and easier to detect. Arsenic, antimony, mercury, and tellurium frequently accompany gold mineralization. Geologists use these chemical signatures to trace fluid pathways and vector toward higher-grade zones. 5. Geochemical exploration methods. Geochemical sampling translates geological theory into measurable data. Rock, soil, stream sediment, and groundwater samples are collected systematically across prospective areas. Each medium serves a specific purpose. Soil sampling detects near-surface dispersion patterns. Stream sediments integrate large catchment areas. Rock sampling confirms mineralization at outcrop. Laboratory analysis, often using ICP-MS or fire assay, produces multi-element datasets. These datasets are statistically analyzed to identify anomalies above background levels. Modern exploration relies heavily on geochemical vectors rather than isolated high values. 6. Geophysical techniques in gold exploration. Geophysics allows geologists to see beneath the surface without drilling. While gold itself is not geophysically detectable, its geological environment often is. Key methods include magnetic surveys, identifying structures and lithological contrasts. Induced polarization, IP, detecting disseminated sulfides. Gravity surveys, mapping density variations. Airborne geophysics enables rapid regional coverage, while ground surveys refine specific targets. Integration of multiple geophysical datasets increases confidence in target selection. 7. Remote sensing and GIS integration. Satellite imagery and remote sensing technologies have transformed early-stage exploration. Multispectral and hyperspectral data allow detection of alteration minerals across vast terrains. Using GIS platforms, geologists layer geological maps, structural interpretations, geochemical anomalies, geophysical results. This integrated approach reduces exploration risk and focuses drilling on the most prospective zones. 8. Drilling and resource evaluation. Drilling is the final test of an exploration model. Diamond drilling retrieves continuous core, allowing precise geological logging, structural measurements, and grade determination. Drill data feeds into three-dimensional geological models, where mineralized zones are interpreted and quantified. Resource estimation follows internationally recognized standards such as JORC or NI 43-101. At this stage, geology transitions into economic decision-making. 9. From discovery to understanding. Identifying gold deposits is a process of interpretation rather than chance. Each discovery reflects a chain of geological reasoning, linking tectonics, fluids, chemistry, and time. Modern gold exploration is a synthesis of classical field geology and advanced technology. The most successful geologists are those who understand not only how to collect data, but how to interpret Earth's history recorded in stone. Gold, ultimately, is not found. It is understood.